Hello students, welcome to my lecture. In this video, I will discuss few important points in the gravitation chapter. These important points will help you solve the problems in IIT-JEE mains, of course in the NEET exam. Okay, so see, this lecture is not something like it is a zero level starting point of the gravitation. It is not like that. So this chapter aimed to revise the important concepts in the gravitation chapter so that you can solve the problems. So last minute revision for your IIT-JEE mains or otherwise NEET examination. So whatever the knowledge you already have, whatever the lecture notes you have, that all together will help along with this video. Okay, fine. Now discuss very important ideas, formulas, conclusions from this gravitation chapter. So first and foremost, the force between the two masses. So if there are two masses will be there, one is m1, another one is m2. Let's say they are separated by some distance r. Then there exists a force of attraction between them. That force of attraction is given by G, the product m1 m2 divided by r square. Okay, simultaneously I'll talk about the not only force and also the energy. So potential energy or interaction energy, potential energy. So the potential energy between these two particles m1 and m2 is given by, that is minus G m1 m2 divided by r. So there is an important relationship between these two quantities. Force F is a vector quantity. It is minus du by dr. I can put r cap as it is a vector quantity. So this relation will help us to determine the force if I know the potential energy. Generally the force will have all the three components: x component, y component and even z component. So here the x component of force is given by minus dou u by dou x and y component of force is given by minus dou u by dou y. Okay, suppose if you want energy from the force, so that energy can be calculated, that is equal to integration of f dot dr. Integration of f dot dr, and of course there is always the reference potential energy, that constant. Okay, so this relation will help you to determine the potential energy from the force, and this relation will help you to determine the force from the potential energy. Okay, so this is all about force and potential energy. Now come to the field, gravitational field. Come to the gravitational field. So the idea of the gravitational field is simply, we define the gravitational field E is equal to the force per unit mass. So that is generally we call it the test mass. This gravitational field strength is also of another meaning, acceleration due to gravity. Another meaning, acceleration due to gravity. Acceleration due to gravity. That's why I give the even symbol G. Okay, so the gravitational field due to the standard objects, for example ring, disc, spherical shell, hollow sphere, solid sphere. So these things are important, you need to remember. Okay, so you take any book, so these formulas are available. So here I revised these two important things. Hollow sphere. For hollow sphere if you take, so there are 2 points you supposed to be discussed. What about for the inside points and what about for the outside points? So one is inside point, another one will be the outside point. For hollow sphere, inside point the gravitational field will be 0. For outside points, which is at a distance of r, the gravitational field for outside points will be simply g mass divided by r square. This is the m is the mass of that hollow sphere. Okay. Then what about for the solid sphere? For a solid sphere, we can think of it is an earth. For a solid sphere, it is an earth. So this is the earth. So what is the answer for inside points? What is the answer for outside points? So for inside points, so E is equal to G is equal to minus or plus. It's minus, of course. It is always attractive potential energy, attractive potential, attractive field. You can put the minus. So we can write it will be G capital M R divided by R cube. Okay. So for inside points. Then what about for outside points? If there is an outside point, this is for inside points. For outside points, we can write, so this is the inside points, for this is for outside points. Outside points, it is simply Gm divided by R square. So if you are coming certain height from the surface of earth, so this is the R will become R plus H. So that time I can write it will be of Gm divided by R plus H whole square. So this I can write simply as Gm by R square divided by 1 plus H by R whole square. So G on the surface, so G value on the surface, it is simply Gm divided by capital R square. Okay. So this formula will give you G variation with height. This formula will give you G variation with depth. So that means variation of the depth in the sense, suppose if I am calculating at that particular point, which is at a depth of D. So that means this distance will become capital R minus D. So that's why I can write here it is Gm divided by R cube into R is simply R minus D. So I can write it is Gm by R square is the G on the surface. So 1 minus D by R, D for the depth. Similarly here also it is G on the surface divided by 1 plus H by R whole square. Okay. So you have to remember all these formulas. So generally questions will be framed on this. Okay. So there is another idea we need to discuss here, it is the gravitational potential. Gravitational potential. Just like potential energy is a scalar quantity, potential is also a scalar quantity. So generally we define the potential difference between 2 points. It will be the potential energy difference or work done to bring something from infinity to certain point divided by the test mass. This work done obviously stored in the form of potential energy by a test mass. Okay. For even gravitational potential also, you remember for ring, you remember for disk, you remember for hollow sphere, you remember for solid sphere. Solid sphere, always remember it is an earth. Solid sphere, you have to remember for this. Okay. For hollow sphere, I'll write. So I am taking an hollow sphere. For hollow sphere, what will be the G value for inside points? G value for outside point. For hollow sphere, G value for inside point is minus Gm divided by R, which is same as that of on the surface point. For outside point, it is simply minus Gm divided by R. So from here what I can include? So uniform potential inside. Uniform potential inside. Then what about for solid point? So solid in the sense sphere. For the solid sphere in the sense it is the earth. So solid sphere. solid sphere, in the sense it is the earth. It is the earth. Then what about for inside points? What about for outside points? So for inside points and outside points it is easy. For outside points it is simply minus gm divided by r. For inside points it is little bit big formula, you need to remember, minus gm by 2r cube into 3r square minus r square. If you think about on the surface it will be minus 3 by 2 times gm divided by r. So obviously gm by r is, so it is on the surface, on the surface means r equal to 0, r equal to r, on the surface, in the sense when I substitute r is equal to capital R. So r equal to capital R I substitute, it will become plus gm by 2r. So answer comes out to be minus gm by r. What about v at the center? Center comes out to be r equal to 0. That time it will comes out to be minus 3 by 2 times gm by r. Obviously it is minus 3 by 2 times v on the surface. So of course when on the surface is the plus, you have to get 3 by 2 times v on the surface. So finally what I want to say here, you remember for force and energy, similarly field and potential, so obviously there exists a relation between field and potential. The field E will be is equal to minus dv by dr r cap. So this is the relation between field and potential. Even similarly potential difference v2 minus v1 will be is equal to minus integration of 1 to 2 into E dot dr. This also will help us to determine the field and potentials. Okay. So this is enough related to force, for potential energy, field and potential. Now we'll go for the very famous laws, that is the Kepler's laws. So that is, before going to the Kepler's laws, similar somewhat like planetary motion for circular orbits. Planetary motion for circular orbits. So something like one object is at the center, heavier one is at the center, which is at rest. Around this another lighter body is revolving. So small m. Generally if we call it as a planet, so if it is called as the sun here, and this will be the planet, something like sun and earth system. Okay. So there are few important points will be there. That few important points I will discuss here. The first question will be, what will be the orbital speed here, with what speed it is revolving. For that I need to write here the necessary centripetal force is equal to gravitational force. So whatever the gravitational force will be there, that will be equal to centripetal force, that is mv square by r. So from here I'll get the orbital speed. So with this idea I'll get the orbital speed will be as square root of gm by r. Okay, this is the idea. Then I want to write for the time period. Time period, as it is moving with the uniform speed, time period is total distance, that is 2 pi r divided by velocity is v. So 2 pi r, that velocity just now I got, it is square root of gm by r. So the time period will become, so 2 pi by root gm r power 3 by 2. I can write it is t square will be is equal to 4 pi square gm r cube. So one of the important result also. So I need to write for the energy, that is kinetic energy is half mv square. This comes out to be g capital M small m divided by 2r. So potential energy I need to write here. Potential energy is minus g mm divided by r. So total energy I can write as sum of the kinetic energy plus potential energy. So obviously if we see total energy, it will comes out to be minus Gmm divided by 2R. So very important results you can see here. So total energy is half of the potential energy. Half of the potential energy. So total energy will be half of the potential energy. Kinetic energy, so total energy is equal to minus of kinetic energy. These are the important results we need to remember. So all you see here, it is 1 by R graphs. This kinetic energy is always positive. Potential energy is always negative here. And total energy is negative. This is even true for the bounded systems. Okay. So related to planetary orbits, so another important thing is also their escape speed. So what is the speed you need to supply here so that it will go to the infinity? It will go to the infinity. So of course at infinity potential energy is 0, and of course we are reaching here, just reaching here. I can write the kinetic energy is also greater than or equal to 0. Maybe 0 you can take. So that means that escape speed I can calculate something like this. So kinetic energy, that is half mv square we are going. Potential energy is minus gmm by r. So kinetic energy 0 and potential energy 0 when it goes to infinity. So from here escape velocity will be square root of 2 gm divided by r. So with this I can calculate the escape velocity. Okay. This orbital velocity, escape velocity, time period, energies, all are important to solve the problems. Okay. So same planets, we go for the Kepler's laws. Kepler's laws. So there are three important laws will be there. Among them, the first law will be the law of orbits. So law of orbits. According to this theory, all the planets will revolve around the sun in elliptical orbits. So that means around the sun all the planets will revolve in elliptical orbits. This is how the ellipse looks like. This is x-axis, this is y-axis, this is the origin. There are two foci will be there. The sun may be at any one of the foci. So this length is known as the minor axis length, and this major axis length. A is the major axis and this will be the minor axis. Assume sun can be here. So this is less than a. This length I can generally call as the AE. So this is the nearest point to the planet and sun. This is the farthest point between the planet and sun. Okay. So this nearest point, let's say r1 distance, it has the velocity v1. The farthest distance generally I call it as the r2. The farthest distance will be the r2, which has the velocity will be v2, something like this. Okay, here this E as an important relation. This E is known as eccentricity of the ellipse. Eccentricity of the ellipse. It is related with there is a relationship between A and B. So E is equal to square root of 1 minus B square divided by A square. Okay. So if you see, the nearest distance r1 can be written as A minus AE. The farthest distance r2 can be written as A plus AE. So this nearest and farthest positions generally known as the perigee and apogee positions. Perigee means nearest, apogee means apart, far away. So according to the law of orbit, all the planets will revolve around the sun in an elliptical orbit. If you even write the ellipse equation here, this is x square by a square plus y square by b square is equal to 1 is the ellipse equation. And sun can be at any one of the foci. So there are two possibilities for the sun. So that means planet anywhere. So I can write S12 planet plus S2p planet is always equal to 2a. 2a is the major axis length. Okay, so try to remember these important conclusions. What is the second law says? The second law says law of areas. So the law of areas means, so aerial velocity constant. Aerial velocity is constant. So aerial velocity constant, that means it is L divided by 2m. So m is here mass of planet, not mass of sun, mass of planet. L is equal to angular momentum of planet with respect to sun. Angular momentum of planet with respect to sun. So you can say like, what is the meaning of aerial velocity is constant? So that means the line joining sun to, the line which joins from sun to planet. Sun is at any one of the foci, sun to planet, this is the planet, sweeps out equal areas in equal intervals of time. So this is the area it is sweeping. So if I calculate this area is delta A, so the time interval from here is delta T. So delta A by delta T will be is equal to same for all. So equal areas in equal intervals of time. This is what the law of areas. Then finally the important conclusion, the important law will be law of periods. Law of periods. What is this? So time period square, time to complete one revolution for a planet around the sun, directly proportional to semi-major axis length cube. So t square is directly proportional to a cube. That proportionality constant comes out to be 4 pi square by gm a cube. So time period is 2 pi by root gm a power 3 by 2. Okay, so this is the law of periods. These three laws are very important. So these are directly required to solve the problems. Apart from this, when the planet is in elliptical orbits, so I can go for the total energy is always constant, that is sum of the kinetic energy plus potential energy. So that is total energy sum of the kinetic energy at any point half mv square, potential energy is minus gmm by r, that will be always constant. Another thing, I can go for the conservation of angular momentum. So the angular momentum at any point I can write as magnitude of r cross p. If I think of 2 points which are nearest to the sun and farthest to the sun, if you notice the angle between them, there comes out to be 90 degrees. For that it is easy to write. So that means m v1 r1 will be is equal to m v2 r2. So at that particular position only the angle between them will become 90 degrees. These two ideas, total energy constant and angular momentum, will play very important role. Okay, so even after solving, I may get the total energy will be, it is something like minus g mm divided by 2a. So this is true in an elliptical orbit. Okay, likewise even I can go for the m1 v1, m2 v2. v1 I can calculate when it is the nearest point, so it will have the velocity that is square root of gm by a into, so nearest point 1 plus e divided by 1 minus e, and v2 farthest point, it will have the less velocity gm by a into 1 minus e divided by 1 plus e. So always check it, v1 r1 will be is equal to v2 r2. Okay, so try to remember these formulas which are directly we can apply to solve a given problem. Okay, yeah, so thank you. So try to remember all the formulas and idea to solve the problems. Thank you very much.